So today we're going to look at u substitution with definite integrals, and the actual integration process is not different. It's just what do we do with these bounds? So um, then you kind of have two options here. So for my first example, I want to find the integral from 0 to 1 of x times x squared plus 1 cubed dx. So let's use u sub to find the antiderivative. If we let u equal x squared plus 1, then du dx is equal to 2x. And you can solve for dx. And we can see what we're working with here. Now, before we, well, no, sorry. Let's first look at, I'm not going to put bounds on this yet. Let's first look at, did we take care of everything we needed to? So we have an x, and we have u to the third. And then instead of dx, we have du divided by 2x. So yes, we did get rid of the x's. So we have the integral of one half the integral of u to the third du. Now here's the thing. The bounds are not still 0 to 1, right? 0 to 1 was in terms of x. That's what you're plugging in for x. So you have two options. Option 1 is to integrate and come up with new bounds. So leave everything in terms of u. If you're going to leave everything in terms of u, you've got to figure out your new bounds. So if u is x squared plus 1, when x is 0, 0 squared plus 1, so a, u comes out to 1. So a equals 1. And the b, the end interval, when you plug in 1 for x, 1 squared plus 1 is 2. So you could say, I'm going to find the integral from 1 to 2 of u to the third du. And then you're not subbing x in anymore. You're saying you have u to the fourth over 4 evaluated from 1 to 2. 2 to the fourth is 16, divided by 4 is 4, minus 1/4. And oops, I dropped a 1/2. Sorry. There's a 1/2 there. There's 1/2 there. And there's 1/2 there. So let's see. So this is 15/4 times a half, so 15/8. Now, that is still the integral from 0 to 1 of x times x squared plus 1 cubed dx. That area is 15/8. Option 2 is to not mess with finding new bounds, but when you take the antiderivative, put it back in terms of x. So you've got 1/2 times, not u to the fourth over u, but x squared plus 1 to the fourth. I said over u, I meant over 4, evaluated from, go back to the bounds in terms of x, 0 to 1. And then you've got 1/2 times, might as well factor out a 1/4, don't you think? So when I plug in 1, I get 2 to the fourth is 16, minus when I plug in 0, which just dinged at me. Hopefully I'm still recording. When I plug in 0, I get 1/4. Oh, sorry. I don't get 1/4. I get 1 because I factored out the 4. So I get 1/8 times 15. I still get 15/8. It does not matter what you do. It's kind of what makes more sense to you. I tend to switch back and forth. It kind of just depends on the problem. All right, example 2. So let's see, we have a 2x minus 1, and this one's going to be a little bit different because the derivative of 2x is definitely not going to give me x. So I'm going to show you a little trick here. So first of all, I don't like that 2x minus 1. Let's let that be our u. Du dx is going to be 2. So du divided by 2 is dx. So let's see where that gets us first. I'm going to leave off the bounds. I'm just going to say a to b. I've got x over square root of u, and then I've got du over 2. So this x did not cancel out. Here's a trick though. It's just a nice little x. And our u has an x in it. So we can still do u substitution. We just need to say, what is x in terms of u? So if u equals 2x minus 1, then u plus 1 divided by 2 must equal x. I can sub that in for that x right there. So I can say, I've got u plus 1 divided by 2 and divided by square root of u. So let's just put the square root of u down there, times du over 2. We've got a 2 times 2 down here. Why don't we go ahead and pull out a 1/4? And then instead of leaving it as u plus 1 over square root of u, instead of leaving it like that, sorry, I don't really mean to put a times or equals there, we need to divide that out, right? Because it's divided by a monomial. So you've got 1/4 times the integral of u to the first divided by u to the 1/2 is u to the 1/2, plus 1 divided by u to the 1/2 is u to the negative 1/2 du. And I sort of dropped my bounds along the way. You could even write still 0 to 1, 0 to 1, 0 to 1. If you're going to do it in terms of x, you need to write your antiderivative in terms of x. I don't know. I'm just writing a to b. And so I've got 1/4 u to the 1/2. When you add 1, you get 3 halves. So you're going to get 2u to the 3 halves over 3. Plus, when you add 1 to that, you get 1/2. So 2u to the 1/2. And then do I want to evaluate with the bounds in terms of u or in terms of x? I think I'd rather just do in terms of u. So now I'm going to go back and say, all right, what is a? X was 1 originally. So that lower a value is 2 times 1 minus 1. So 1. And the b value is 2 times 5 minus 1. So 9. So the integral is from 1 to 9. Just seems easier than plugging a 2x minus 1 back in. All right, so what do we have? We have 1/4 times what? When you plug in 9, you're getting square root of 9 is 3, to the third is 27, divided by 3 is 9, times 2 is 18, plus 2 times 3 is 6, minus, now you've got to plug in 1. 2 times 1 divided by 3 is 2/3, plus 2 times 1. 1/4 times 24 minus 2/3 minus 6, or I'm sorry, 2/3 plus 6/3 is 8/3. And we're subtracting that. And then we've got, oh, maybe it'd be nice to do 6 minus 2/3. That seems easier than doing a common denominator first. 5 1/3 or 16/3. All right. And if you can, instead of writing A and B's, it probably just makes sense to go ahead and just find the U bounds and just go with it. Or if not, keep it at 1 and 5 and sub back in. But I think that I usually find the new bounds. This one looks complicated. Let's see. Let's look at what we have. We have like a y plus 1 and a 1 minus y. Those derivatives don't seem like they're going to cancel. What's up with this minus dy? Well, that's in there because if you let u equal 1 minus y, we're going to get a minus dy. So we kind of see that. Although you are allowed to take this negative, just put it out here to begin with and be done with it. So what do we want to do? I think this is the inner function. I'm going to go with it. U is 1 minus y. Du dy would then be negative 1. And du divided by negative 1 would be dy. Or du would be negative dy. Again, that's why that's in there. Let's say I haven't gotten rid of any negatives. That doesn't help me with the y plus 1, but remember, when the variable's out here and it's just a nice y, it's not a y squared or anything kind of crazy, it's pretty easy to sub back in and say, well, what is y plus 1? So when you're doing your substitution, you've got negative 2 pi, the integral from, all right, let's see. If we put in 0 for y, we get 1. If we put in 1 for y, we get 0. Oh, that's weird. That's backwards. Y plus 1 square root of u negative dy. Oh, no, just kidding. Negative dy, but dy is negative du. So negative dy is just du. All these negatives. Hopefully I'm not confusing you. Okay, and then what's this other trick we need to remember? There are two things we need to think about. We are not supposed to have backwards, what I consider to be backwards bounds. B cannot be lower than A. Remember, you're allowed to flip that around as long as you put a negative out in front. This is now positive 2 pi from 0 to 1. And then what about this y plus 1? We know that u is equal to 1 minus y. Let's solve that for y. Y, if I add that over here, is equal to 1 minus u. And y plus 1 is equal to 1 minus u plus 1, which is 2 minus u. So I have 2 minus u times square root of u du. I should distribute that square root of u through 2 square root of u minus u to the first times u to the 1/2 is u to the 3/2 du. I can integrate separate terms here. So I've got 2 pi. Remember, I already switched my bounds to be in terms of u, so I'm good to go. When you add 1 to this, you get u to the 3/2, 2/3 times that. There was already a 2 there, so 4/3 times u to the 3/2 minus, this will be u to the 5/2, and then it'll be times 2/5, evaluated from 0 to 1. When you plug in 1, you get 4/3 minus 2/5 minus, when you plug in 0, you get 0 minus 0. It's always good to double check that just in case. 2 pi times 20/15 minus 6/15. 2 pi times 14/15. 28 pi over 15. All right, next example. Seems like we should make u equal to x squared minus 8. Du dx is going to be 2x. Du divided by 2x is going to be dx. Let's fix our bounds as well. A is going to be 9 minus 8, which is 1. And B is going to be, that's a 6. B is going to be 36 minus 8. 36 minus 8 is 28. All right. So now we have the integral from 1 to 28 of x over 3 square root of u times du over 2x. X's cancel, that's a good sign. You have a coefficient of 1/6 that you can factor out, constant of 1/6. And then we can just make it u to the negative 1/2 du. When I add 1 to that, I get 1/2. So 2 u to the 1/2 evaluated from 1 to 28. So this is 2 radical 28 minus 2. Radical 28 is really 2 radical 7. So 4 radical 7 divided by 6 is 2 radical 7 divided by 3. And then minus 2 6 is 1/3. Or you could make it 2 radical 7 minus 1 all over 3. Same thing. All right, so let's see. U would have to be 2x. Du dx would be 2. Du divided by 2 is dx. On this one, do we really need to use new bounds? This one's not so bad, so you could keep everything. It's not hard to rewrite just back in terms of x, but I'll just keep things consistent. So a is negative pi over 4 times 2, so negative pi over 2. And b is pi over 4 times 2, so positive pi over 4. Positive pi over 2. So we've got the integral from negative pi over 2 to positive pi over 2 of sine of u, and then du divided by 2, remember. So you're going to have a 1/2 out front. And then the antiderivative of sine is negative cosine of u. Since I changed my bounds, I've got to keep that as u. All right, well, cosine of pi over 2 is 0. So you've got 0 minus cosine negative pi over 2 is 0. So this one comes out to 0. Remember, you're allowed to get that. Think about this. The sine x function, which hasn't been shifted horizontally, it is an odd function, right? It looks something like this. I know the period is changed, but basically we just found, I know it's not this entire area, but we just found symmetric pieces of area, one negative, one positive. So that makes sense. All right, we have to be careful on multiple choice questions. Pay attention to some of the details, like the limits of integration. So given that f of x is an even function, excuse me, given that f of x is an even function, remember that means you've got y-axis symmetry. This area is equal to this area on the other side. And the integral from 0 to a of f of x dx is 3. Find the value of the integral from negative a to a. So again, if this from 0 to a, this is 3, then from negative a to 0 is 3. 3 plus 3 is 6. Given that g of x is an even function, so same symmetry, and the integral from 0 to a is 5, I always just end up drawing this. So 0 to a, this is 5. Find the value of a to a. Now be careful here. A to a, same bounds, that area is 0. So all of this other information was irrelevant. H of x is odd. Odd is like something like this. 0 to a, that area is 8. Find the value from negative a to a. That has to be, since it's an odd function and we know it's symmetric, that has to be an area of negative 8 plus 8, net area of 0. All right, so part of your homework tonight is to work on this mixed review. And then I think we also have a textbook assignment that goes with this as well. But the mixed review is something that I'm going to check for completion on Monday.